Hi guys, Mr. Rocco again. This will be the second video for this week, and this one is going to be all about air pressure and wind and how the air pressure affects the wind. So let's review cold air versus warm air, which you see right here. Again, cold air is high pressure. Remember, high rhymes with dry, and think about when you usually have dry skin. In the winter, when it's cold outside. So cold air is a high pressure system. Low pressure is warmer air and more moisture. Storms, like what we have coming in tonight and tomorrow. Air pressure is measured with a barometer. I went over that last week in the first weather video I talked about. You should know those instruments. Again, thermometer is for temperature, a barometer is for pressure, an anemometer is for wind speed, a wind vane is for wind direction, and a psychrometer is for humidity. Now, if you're at the ocean, or what they call sea level, the standard air pressure is, they call it 1 atmosphere. It's equivalent to 29.92 inches of mercury, or 1,013.2 millibars. A very, very cold day, like we've had recently, those are extremely high pressure systems. The meteorologists will use the term the polar vortex. That's a very strong Arctic high pressure that slides down out of the North Pole and will come down here into the Northeast. Those really, really cold air masses have a very high pressure, 1,050 millibars. That would be considered a very strong high pressure system, extremely cold air, which we've had recently. A very powerful hurricane, and I've listed some storms in our history with very low pressures. Again, meteorologists look at the pressure in a hurricane. As the pressure drops, that indicates the hurricane is strengthening. It's getting stronger. So the lower the air pressure, the more powerful the storm. And if you watch that video I linked on Canvas about flying, showing those guys flying through the eye wall of a hurricane, you'll see they use a barometer to measure the air pressure. And that's what they're looking at. So every 3 hours, they're going to measure that air pressure in the hurricane to see, is the pressure going up or is the air pressure going down? If the pressure continues to go down every 3 hours, the storm is getting stronger. And so some of your very, very strong hurricanes in history go back to Katrina in 2005. That had an air pressure of 920 millibars. That's very low. So Katrina was a very powerful storm. Superstorm Sandy, 2012. That was also pretty powerful. 940 millibars. Hurricane Michael, that hit Florida a couple of years ago, 2018. That was 919 millibars. Camille, 1969. That hit the Gulf of Mexico, the Gulf Coast. That was 900 millibars. That was a very strong storm, 1969. Prior to myself being born, I was born in 71, but still, nonetheless, that was a strong storm. So when it gets down into the low 900s, those are pretty powerful. The hurricane, the nor'easter that's coming at us tonight, tomorrow, Monday, Tuesday, with this big snowstorm that I'm looking at now. I just been checking the weather. Anywhere from a foot up to 2 feet is what we're looking at. That's the forecast. The pressure on this nor'easter will get down in the 980 range. That's pretty strong for a nor'easter, for a snowstorm. That's pretty powerful. So it'll be in the 980 range. This was an assignment you had to do a worksheet last week on pressure conversions. So in your ESRT on page 13, I would definitely add this to your reference table just for future reference if you haven't done so. The left side counts by millibars. The right side counts by inches. Just be careful with the scales. The left side, each line on the left side in millibars is 1 millibar each. Like if this is 1,024, this would be 1,025, 26, 27, 1,028, 29, etc. The right side counts by 1/100th each, 0.01. So if this is 30.10, the next line up would be 30.11, 1.2, 1.3, 1.4, 1.5, etc. So just be very, very, very careful when you're converting from inches to millibars or millibars to inches. Most of you did very, very well on the assignment last week, so just keep that in mind when you do conversions. This kind of barometer, obviously, you can't have in school because it has mercury in it. Mercury, being a toxin, is illegal to have in a science classroom. But mercury is a very sensitive fluid when it comes to air pressure. And so what this basically is, you've got a dish here filled with mercury and this tube in a vacuum. So there's no air inside, and that's going to allow this mercury in this tube to go up and down depending on the air pressure. There would be markings on this tube that would measure the pressure. And so let me go back for a minute to this slide. So standard pressure is 29.92 inches of mercury. And so on this tube, there would be markings there that you'd be able to read how many inches of mercury you have in this tube. Basically, the way this works is when there's very cold air, right, high pressure, if the pressure outside was high, so I'll put an H here, that's going to create strong pressure pushing down on the fluid in this reservoir. So if it was a cold, dry day, high pressure, it's going to push down on the fluid in the mercury in the dish. That's going to cause this mercury to now go up the tube. And that's going to raise the number, which will then read this level be higher. And that would tell you it was a cold day. If it's a low pressure kind of day, again, low pressure is less warmer air, moist air. Let's say, again, a storm's coming, right? I would know that the mercury inside this tube would actually start to go back down the tube and fill in the dish down here. And so you'd be able to tell that the pressure was dropping. That just talks about mercury barometer, so I'll skip that. Now, this kind of barometer I actually have in my classroom. I did not put it out last week. I'll try to get that set out on my classroom so you can look at it, those of you that come to school. It's called an aneroid barometer. It's a very easy way that it works. On this little, over here to the right of the can, these are called bellows, bellows. It's written right here. And so on a high pressure day, what happens is these bellows act like an accordion. Cold day, the bellows would squeeze together. There's a bunch of levers and arms that are connected to this. And then eventually this arm right here has a little ink that you drop here on the end. This can has a piece of paper that spins around very slowly. There's lines on this can every 4-hour increment. And this can will rotate around, and the pen arm will go up or down depending on the pressure. So since it's been very cold the last couple days, that's going to cause these bellows to squeeze together. This arm will then move up this way. And so the arm will be up here more in this area. The arm would go like that, more like a high pressure day. Now that we have a storm coming, a storm is low pressure, these bellows right here would relax, they would expand a little bit, and that'll cause this needle that was once up here to start to go down like that and drop. And so, there's a little ink, like I said, on the end of this pen arm here that will leave a line. So you'd see a line, like this might show you, oh, Mr. Rocco, it's a cold day. And, oh, look at the lines going down. That means the storm's coming. And then, oh, wait, we're going back up to a cold, dry day. And that'll just rotate this can. It takes 1 week for the can to rotate a full circle. And then what you basically do is just rip this piece of paper off and you attach a new piece of paper to the can. And, yeah, I have one of these in my classroom. So I'll set that up for you so you guys that come to school can take a look at it. That's called an aneroid barometer. Now, every major city across the United States is going to have a weather station. They are recording the pressure, and that pressure gets reported to the National Weather Service every 3 hours. It's all now with computers and everything. It's done digitally. So every 3 hours, the pressure, let's say for Poughkeepsie, Albany would be some of the cities around here, New York City, obviously, Buffalo, Syracuse. They're going to upload their data to the database at the National Weather Service every 3 hours, and then all that information goes into the computer, and the computer is able to draw automatically isobars. Now, we talked about iso lines back in the fall when we did contour lines, right? If I wanted to show a hill, right, it was circle, inside a circle to show a hill or a mountain. Those were equal elevations. So now isobars, because the instrument that measures pressure is a barometer, isobars connect equal pressure. And so they're usually drawn every 4 millibars. And you can see from this map. So right here in the center of the country, there's a low pressure there. That'll be an L. And then you see this first isobar, all the cities around the low that have a pressure of 996 millibars. And obviously, if the low is in the middle, that's the lowest pressure. As you work away from the low, right, the numbers are going to go up. And they're going to draw lines every 4 millibars. So this is 996. The next line out, you add 4 to that. That's why you got 1,000. So this would be the 1,000 millibar isobar. Then you keep adding 4. 1,004 millibars. That would be this one. And then 1,008, and etc. And so it's like ripples on a pond. If you throw a big giant rock into a pond and you get the ripples on water, that's the same idea with isobars. You're going to get these, what they call concentric circles, like one circle inside another, inside another, inside another. Just like when we showed a hill or a mountain on a topographic map. Now, how do I know where the wind is? And this gets into what causes wind. Wind is created by what's called a strong pressure gradient. The word gradient shouldn't be new. Gradient means slope, or the change in elevation over distance. In this case, that's an elevation gradient. In this case, we're talking about a pressure gradient, which means I need a very big difference in pressure between a high pressure system and a low pressure system, and they're not that far apart from one another, relatively speaking. And so that creates what's called a strong pressure gradient. You want a very strong high pressure, and you see over here I'm kind of circling this high pressure. This pressure might be very, very high, like 1,040 millibars would be a strong high pressure. Let's say this storm over here is a very strong low pressure. This might be 950 millibars. So you're talking a difference of, what, 90 millibars between them, which you might say that's not a lot. In the world of pressure, 90 millibars is a huge difference in pressure. Like, words can't describe it, but 90 millibars difference between a high and a low is very, very big pressure difference. And these two systems are not that far apart. They're not like one on the East Coast, one on the West Coast. They're fairly in the middle of the country. And so what happens is you've created a strong pressure gradient. Big difference in pressure between a high and a low, close to each other. And so what you're going to notice are these isobars. See, you can see these white circles around the low pressure are very, very packed together. That indicates a strong gradient or pressure gradient. Very similar, or it is similar to when we did topographic maps, right? If you had a mountain, and let's pretend this was a mountain, how did I know the land was steep, right? You knew because the lines were close together, so you knew which side of the mountain was steeper. Same idea here. That was a steep elevation gradient. Now we're talking about a steep pressure gradient. And so typically around a storm, a low pressure system, if you see a lot of packed together iso lines, that indicates which side is strong winds. Now in this low pressure, you can see they're pretty packed together all the way around. So that means the wind is going to be pretty strong on all sides. That might not always be the case. Like you might have isobars on this side that are packed close together, and over here they're kind of spread out. Then you would know, oh, on the west side of that low pressure, on this side it's much windier. Wind is generated by a difference of pressure. Wind always goes from high pressure toward a low pressure. So it blows away from a high and blows into a low pressure. And so you would have strong winds coming from the west blowing toward this low pressure here. I'm going to put a couple of links again on Canvas. This one's really cool. I don't know if you know Jim Cantore. He's on the Weather Channel, one of their more popular weathermen. And he went into this wind tunnel. It's at Virginia Tech University. It's a hurricane simulator, and he goes in there, and this is really cool. I recommend you watch it. He harnesses himself in the wind tunnel, and he gets the wind speed up to Cat 5 winds, 150 something miles an hour, and you could see him trying to stand up against the force of the hurricane strength wind. So it's pretty cool. I'll put this link on Canvas, so please get a chance to watch that. This one I'll also put on there. This one's very short. Mount Washington, which is the tallest mountain in New England. It's up in New Hampshire. I'll show you a map on the next slide there. This guy stands up against the wind up there is always on the top of Mount Washington, can be over 100 miles an hour. So this guy is trying to stand up against 109 mile an hour wind gusts at the top of Mount Washington. So I'll put that link also on Canvas so you can watch that. So here's where Mount Washington is. So you got Vermont, New Hampshire, and right about here, Mount Washington sits at 6,288 feet, which is nothing compared to the West Coast mountains, the Rockies, etc. But for the Northeast, that's the tallest mountain. Very extreme weather Mount Washington has. It can be extremely windy, like I said, hurricane force winds, very, very cold weather. So I'll put that link on Canvas. Just to compare Slide Mountain, which sits in the Catskills, not too far away from us. If you go a little farther west across the river, that's 4,000 feet, a little over 4,000. And Mount Marcy, which is the tallest mountain in New York State, sits in the Adirondacks at 5,344 feet. So Mount Washington is almost 1,000 feet taller than Marcy. So again, the same rule is going to apply to wind as when it came to a slope of a mountain. This is going back to a little review of the topographic maps. You knew over here that the land wasn't very steep up here because the lines are further apart. So this had a low elevation gradient because the topographic lines were spread out. The land is flat, no slope there. You knew down here this was a high elevation gradient because steeper slope because the topographic lines were packed together, contour lines. So the same rule will apply again to wind. If this was isobars to show pressure, this would indicate down here that it was very, very windy in this part of the map. Up here would indicate that it was very calm, no wind up here. And so you use the same rule when it comes to isobars as you would to contour lines. The formula for gradient is the same. So gradient, if you notice on your reference table on the front page, they only give you the formula. They just write gradient. But gradient could be anything. Again, in this case, we're doing a pressure gradient, but it could be elevation. So it's the same exact rule. We were doing, let's say we had a topographic map, and you had a location over here, A, and you had a location over here, B, and I said, what's the difference? What's the elevation, or the gradient, I should say, between A to B? You needed the change in elevation divided by the distance between A to B. Same rule applies here, except instead of a difference in elevation, you're substituting this right here, the difference in pressure. It's the only difference. The distance is still down on the bottom, measured in miles or kilometers, but instead of a change in elevation, just switch out elevation and put pressure here. So let's just do a real quick example. Let's say New York City, they have their barometer and they measure an air pressure of 1,014 millibars. So that's the pressure in New York City right now. Let's say Albany has their barometer set up and they get a pressure of 1,004 millibars. And so you want to find the pressure gradient. The distance between Albany and New York City is 150 miles. So you've got the pressure in New York, you've got the pressure in Albany, and you've got a distance of 150, and we're going to try to calculate the pressure gradient. Again, this is just like when you did contour maps, topographic maps, except now instead of elevation, we're substituting a pressure. So the first thing you have to do is subtract the pressures, right? 1,014 minus 1,004 is a 10 millibar difference. So there's a 10 millibar difference. You're then going to divide the change in pressure over the distance, right? 10 millibars divided by 150. I get my calculator. It's going to be a very small number. 10 divided by 150 gives me a pressure of 0.0666667. So I'm going to carry it out only to the 100th place. This 6 makes this one go up to a 7. So I'm going to round that up to the 100th. It would be 0.07 if I round that properly. And my units, again, are millibars, because that's what was up here, per mile. So that means the difference in the gradient, I should say, the pressure gradient between New York and Albany is 0.07 of a millibar per mile. Again, same exact formula we used when we did topographic maps. Just substitute up here instead of elevation, you're putting a pressure number. Wind, by definition, is the horizontal movement of air across the surface. So if this is the ground, wind is going with the surface, one way or the other. And that's why I stress horizontal. Air that moves vertically is not wind. It is moving air, but it's not called wind. Air that goes up and down is convection, right? Remember we did that in the last week's notes, last week's videos. Circulation, right? Cold air sinks, warm air gets pushed up and rises. So that up and down motion is convection. It's not called wind. Actually, to be technical, it's called updrafts and downdrafts. Very easy. So when you're talking about a tornado and you've got wind that circulates up and then circulates down to get that rotation going for a tornado, that's what the meteorologist will call those air movements. Instead of wind, they're going to call it updrafts and downdrafts. So wind has to go with the surface. It's a vector. What does a vector mean? We touched on that way back in the fall, so you might not remember. A vector has to have two things: a number, a magnitude, and a direction, compass direction. So wind is always named for the direction it comes from. So if you're watching the weather channel or, listening to the weather, reading the weather, and they say today it's going to be a cold day, we have northwest winds at 30 miles an hour. So that is telling me that the wind is coming from the northwest. So if you got your compass rose, northwest is up here, right? It's coming from the northwest, blowing toward the southeast, and pretty fast at 30 miles an hour. That's what makes it a vector, because one, it's telling you the speed. Two, it's telling you the direction the wind is coming from and the way it would be heading, which would be opposite. So be careful when you are talking about a wind. Clear those again. Typically a north wind or a northwest wind, I might have mentioned this in another video. Northwest winds and north winds tend to be your colder winds because they're coming out of Canada. And so a north wind, that's northwest, there'll be a north wind. Any winds coming from that direction are coming up from Canada heading toward us. Typically a south wind or a southwest wind, those winds tend to bring warmer air. And sometimes I will mention it to kids. I'll say, Mr. Rocco, it's going to be a warm day today or a cold day. I'll say, don't even look at the high temperature. They'll usually tell you today they predict it to be whatever. If you want to just look at the wind direction, you could tell what kind of day it's going to be just by the wind direction. So if they say today we're going to have north winds, then it's going to be a cold day. If they say today we're going to have a southwest wind, then it's going to be a warmer day. I usually will get into that discussion with my wife when I go across the Kingston-Rhinecliff Bridge, right? If you ever go, let's say you're on the Rhinebeck side and you're heading toward Kingston, and right when you get about halfway over the Kingston Bridge, there's a big American flag right there. Well, when the flag is pointing south down toward Poughkeepsie, that would mean the wind is coming from the north. That's a colder day. So if you've noticed, if you've gone over the Kingston-Rhinecliff Bridge in the last several days, that flag has been pointing in the south direction, which is indicating all that cold air that's been funneling down, from Canada. Now, if we start to warm up, which the forecast is by later in the week, we might get a little bit warmer, maybe back above freezing and get up into the upper 30s near 40, then you might see the flag pointing north toward Albany. That would indicate a warmer day. So that's one way you can tell what kind of day it's going to be. So wind is always named for the direction it comes from. Again, wind is caused by a pressure gradient. You need a very strong high pressure and a very strong low pressure, creating a big difference in pressure. So this is very low. Like I said, let's say this low is 950 millibars, and this high pressure is 1,040 millibars. So again, that's a 90 millibar difference between this high pressure system and this low pressure system. That creates a large pressure gradient. That's going to generate wind. And that just shows the isobars. So what you're seeing there are the isobars. Now, if you look up here, you say, well, is it windy way up here in this section? No, because the isobars are further apart from one another. But if I said, put an X right here, would it be windy at letter X? Absolutely. How do you know? The isobars are very packed together. So again, if you listen to the meteorologists when they're talking on television, they do give you these little mini weather lessons from time to time. That's one way I learned weather from an early age, just listening to the weather when I'd watch television and they'd explain weather to you, and say, we have a strong windy day. Look at the packed together isobars, blah, blah, blah. So that's how Mr. Rocco picked up on a little bit of weather way back when. But yeah, weather meteorologists that explain stuff I appreciate, and I respect them because they'll give you little lessons on weather. They won't just say, here's the weather, then you go, boom. They'll give you a little lesson, though, which is kind of nice. So closely packed isobars, very windy. So you can see way down here in this southeast corner, right, the isobars are really packed together. That would indicate a lot of wind. Not as windy over here because they're further apart, as you see in this picture. So this would indicate that it's not a windy day. Typically around high pressures, you don't get a lot of packed together isobars anyway. Usually it's around a low pressure, but just to show the isobars are spread out here, so calm, no wind here. And this is again a typical map. You can see I pulled it off the Weather Channel. So you had a low pressure here, which is heading out toward the northeast. And this is typical of winter weather. We get a lot of snow, and then we'll get a lot of blowing and drifting snow. And again, you're going to see that happen with this storm that's coming in. Yeah, we get 1 foot to 2 feet of snow, and this snow will be very light, very fluffy kind of snow because it's so cold. So because we have a lot of dry air in place, this won't be a wet snowfall. Kids will always ask me, when do you usually get the wetter snow? Typically, you're going to get a wetter snow in March because, remember, think about what's going on in March. The sun is getting higher. The days are getting longer. We have a stronger sun in March. So when we get those March snowstorms, sometimes we get a good old blizzard in March. That tends to be a very wet, heavy snow. There's a lot more water content. The temperature also is probably just hovering at 32. Now, these last several days, and I know today it's been like in the single digits, teens, maybe got up to 20, but that's way below freezing. So the air is very cold, and so the snow that we're going to get with this big snowstorm is going to be a dry, powdery snow. So when we get 30, 40, 50 mile an hour winds, you're going to see it blowing and drifting all around. So it might be very difficult. I guarantee you it'll be difficult trying to clear your driveway and your sidewalk because the wind, you're going to go through and try to shovel and snow blow it away, and it's going to blow right back into your face. So just be careful out there with this storm. Where, I tend to wear not only just a hat, but like a face shield, some kind of, bundle up the face because you don't want to get frostbite. It's brutal when you're trying to clear that driveway. So anyway, very windy here. You see this storm pulling away, and then you see these packed together isobars, which indicates a lot of wind. Over here in the middle of the country, you can see it's not very windy. There's no isobars, or they're very, very spread out. Again, wind is like energy. So remember we talked about source to sink. A source is a higher temperature. I'll write the word source there. And a sink, that's a source. A sink is a lower temperature. And energy always flows from something hot to something cold. Well, same thing with wind. Wind has to go from a higher pressure system toward a lower pressure system. So it goes out of a high and goes into a low pressure. So wind always, I stress that, always goes out of a high into a low. What controls the wind? The Coriolis effect. Now that goes back to astronomy. Because the Earth is rotating, we are going to curve the winds a little bit. And we'll get more into this in next week's video. But basically, in the northern hemisphere, winds are going to curve to the right. In the southern hemisphere, winds are going to curve to the left. And that's again controlled by the Coriolis effect, which is in turn controlled by Earth's rotation. And lastly, sea breezes and land breezes. So a sea breeze is going to happen during the day. And we talked a little bit about this when it came to specific heat. Remember I said water takes a long time to heat up because it has a high specific heat. And so during the day, you're going to have colder air over the ocean, which again, cold air is high pressure. So you're going to create a high pressure cold air over the ocean. You're going to have a hotter, warmer air mass, which is low pressure, sitting over the beach, over the land. And so during the day, again, because remember, wind has to go from high to low, the breeze is going to blow from the ocean, or from the sea, toward the land. And again, remember, wind is named for the direction it's coming from. So since it's coming from the sea and blowing toward the beach, it's called a sea breeze. Sometimes meteorologists will call it an onshore breeze. So onshore breezes are actually going to carry moisture and bring moisture onto the shore. I know I've spoken to Mr. Boucher. If you have Boucher, maybe Mr. Moore talks about it as well in Global. When you talk about monsoons and India, a country like India, other countries have monsoons as well, but he'll mention India and talk about the rainy season, which tends to be in the summertime for a place like India, because what happens is the continent of India, the land itself gets very, very hot. The Indian Ocean stays cool, and there's that creation of high-low pressure. And so the wind is going to blow from the ocean toward the land of India, carrying all that rain and moisture onto India. And so during the summer months, India goes into their rainy monsoon season. Now, in the wintertime, this time of year, it's the opposite. The land stays cool, but the ocean actually stays warmer. That's like swimming at nighttime. And so they get an offshore breeze or a land breeze, which strips India of its moisture, and there creates a dry monsoon season. And so India will go through these periods of wet and dry monsoons. And that's all because of high pressure, low pressure situations. So let me go back to this sea breeze situation. So you have, again, cold air sitting over the water during the day now. See, the sun's out. Sun's a happy guy. Cold air over the ocean. You've got warm air over the land. That's going to put a high pressure here. I'll put H. That's going to put a low pressure here. Warm air is less dense, low pressure. And so during the day, the breeze is going to blow onshore, sea breeze. That's going to create that convection. So the cold air is going to swoop in. You're going to feel a nice cool breeze. That's why you go to the ocean during the summer months, right? To feel that cool ocean breeze, to cool off from the heat of inland, right? Rhinebeck being way far from the ocean, right? So you go to the beach to cool off. And then that hot air is going to get pushed up. Here's your convection. It's going to circle around, got your convection cell, and then that cold air is going to swoop back down again and start the whole process again. And this just shows the same thing. So you got your high pressure over the ocean during the day. You've got your low pressure hot air sitting over the land. The wind is going to blow onshore, sea breeze, and that's going to create that convection. Here goes the hot air rising, goes up, cools, condenses, forms the clouds. I talked about that in the last video. And then that cool air is going to sink, come back down, and start the whole process again. And that just shows the same thing. So high to low, there's the convection, circling back around again. So you get an onshore breeze or sea breeze during the day. And, this picture shows that during the day. You could tell from the trees, especially if you look at these trees over here, you see the way they're kind of bending. These palm trees, they're bending inland, right? Ocean's out here. And so you're getting a sea breeze during the day. The wind, you'll see your palm trees tend to bend inland during the day. And then obviously at nighttime, these branches and stuff are going to bend offshore. And that's that whole swimming at night situation. So now at night, and again, this goes back to specific heat, the land is going to be cooler, right? It's actually cooler when you get out of the pool at night. The water is actually going to be warmer. That's your low pressure. So you've got cooler, high pressure over the beach. You've got a warmer air sitting over the ocean. And so now again, because wind blows from high to low, the wind is going to go from the land toward the ocean, or what they call a land breeze, or meteorologists call it an offshore breeze, which again would create a dry situation for your monsoons. Something like India in the winter months would have their dry monsoon. And so you see the whole convection cell actually does a reverse. Now that doesn't happen right away. I'll get kids say, does it happen as soon as the sun sets? No, the sun has to set, and then I usually you might see it after a few hours. So if the sun goes down, let's say 8 p.m., you might have to wait till 11, midnight. It could take 3-4 hours before eventually this thing circles the other way. And now again, the high pressure sitting over the land where the cooler air is, and the warmer water has the low pressure, and the breeze will eventually switch and go offshore. And then the convection cell again does the same thing. It's going to rise the warm air, come up here, sink back down as a cool air mass, and just keep going around and around. But it doesn't happen instantaneously right after sunset. It takes several hours, but that's what happens at night. You get the offshore breeze or the land breeze. And so this shows the same thing. You got the cooler breeze, cooler land, and you've got the warmer water. And so you're going to create high pressure to low pressure going this way now. This would be your H. This would be your L. Low pressure is always warm, right? High pressure is always cool, going this way. This video, again, I'll put the link on Canvas. If you ever saw the movie Castaway, and this is just a scene from the movie where Tom Hanks, if you've watched Castaway, and he's trying to get off the island, but he's having a hard time because the waves, those big waves, keep pushing him back. The one time he takes the raft, and the raft kind of knocks him over, and he cuts his leg on the coral. Well, he's standing there on the beach, and he's waiting for offshore breezes. And that's what he needed. And so you see him kind of standing, let's say this was his island here, minus the house, and he's right there on the beach, and he's got that, the doors that have the wings on them, if you recall from the movie, where they were from the airplane, I guess, and he has them standing up on the beach, and then all of a sudden the breeze switches from an onshore breeze to an offshore breeze, and you see the doors fall over this way. They flop out toward the ocean, and all of a sudden you see his kind of eyes go up like, oh, it's time, because he realizes, oh, the breeze isn't coming in anymore. The breeze is now going offshore, and the waves that are coming in like this, he knows he's going to have a little bit of extra help from the offshore breeze. And so he realizes it's time to get his raft ready, and he gets those airplane doors. He uses them like a little sail almost, is what he does. I mean, I know it's a movie, but, you know, that's the whole idea behind it, that he's using these land breezes, these offshore breezes, to try to lift him up over those big waves to get him out into the ocean, which eventually he does and then gets back to life. But yeah, so I'll put that link to that section on the video there, or I'll put it on Canvas, that piece of the video that shows those land breezes that he uses to get himself off the island after, I think he's on there for like 4 years or something like that. Okay, that's it for that, and so you've got the 2 videos to watch. You got a couple assignments to do. There's a weather lab. You got to use Explorer Learning to help you. It's got one of those gizmos. It's not a hard lab. Just take your time on it. Read the steps carefully. Use the gizmo to help you answer the questions and fill in the data on that. It's a Google Doc, which is on Canvas, and that is it for this week. Please stay safe during this storm. Again, I'm finished up recording. It's almost 5 p.m. on Sunday, but be safe. You know, make sure you have enough you know, gas for your snowblower. I would have your generator ready. You know, things like that. Flashlights, batteries, things that you need to, in case you lose power. You know, obviously stay off the roads. They're going to be pretty messy for the next couple days. This is not one of these little tiny little snowstorms. This is a pretty big storm. I've been watching it for the last several days. So just be safe, be smart, and stay warm. And I will talk to you soon.